For most of your life, you have been told the same story about black holes, that they are monsters, that they hide in the dark, hungry, lurking, waiting to devour everything that comes near them, that they are holes, empty pits in the fabric of the universe, sucking down stars and worlds and light itself into some terrible nothingness from which nothing can ever return. That they are the most violent and dangerous things in the cosmos. Almost none of that is true. Tonight, I want to tell you, gently, what black holes actually are. Because the truth is stranger and softer and more beautiful than the story we have all been told. The real black holes of the universe are not hungry monsters. They are not even holes. They do not suck. They do not chase you down across the galaxy. They are not dark. Many of them are, in fact, the brightest objects in the cosmos. They are not violent at their hearts. The largest of them are profoundly, almost unimaginably calm. They are not the enemies of life in the universe. They may, in a quiet way, be the very reason any of us exist at all. If you stripped away every horror movie, every science fiction novel, every dramatic documentary that has shaped how we imagine these things, and looked carefully at what they really are, what astronomers and physicists have slowly, patiently uncovered over the last 100 years, what you would find is something far closer to what we, on Cosmic Nocturne, mean by gentle wonder. Not a monster, a mystery, not a void, a place where everything we think we know about space and time, about beginnings and endings, about what is solid and what is empty, gets very softly turned around and shown to be stranger and more beautiful than we ever guessed. So here is the question I want us to carry together through the quiet hours ahead. If the most feared thing in the universe, the black hole, is not what we have been told it is, then what is it? And could it be that this thing we have called a monster has been, all along, one of the most extraordinary and gentle features of the cosmos that holds us? Welcome. This is Cosmic Nocturne. Get comfortable. Close your eyes if you'd like. You don't need to watch tonight, only listen. Together, we are going to take the story of the black hole gently apart, piece by piece, and put it back together as it truly is, until what you have been told to fear becomes, by the end of the night, something you understand, something that holds a quiet place in the cosmos you live in, something that you can rest beside, peacefully, in the dark. Let your breathing slow as we begin. There is nothing here you need to remember by morning. This is a slow, gentle drift through the truth of black holes, patient, unhurried, soft, told gently enough to carry you toward sleep. You can let your eyes close. You only need to rest and let the real, quieter, stranger truth of these things settle softly over you. Let each breath grow a little slower, a little deeper. The black holes of the cosmos have been quietly being what they truly are for billions of years already. They can keep being it while you rest. So settle in. There's no hurry. Tonight, we are going to learn what these things really are. Let us begin with the very first thing you have been told about black holes that turns out not to be true. They do not suck. Not anything. Not at all. This is perhaps the most common image we carry of them, taught to us by countless films and stories. The great cosmic vacuum cleaner, pulling stars and planets and unwary spaceships toward itself across the void. An inescapable drain at the heart of the galaxy that nothing can resist. It is a dramatic image, and a frightening one. And like so much else we have been told about black holes, it is wrong. Black holes do not suck things in any more than the sun sucks things in, or the Earth, or your own body. They are objects with mass. They have gravity, like everything else with mass has gravity. But gravity, at any distance, depends only on mass, not on what the mass is made of or how it is arranged. If you were to take our sun this very night and somehow compress every single atom of it down into a region only a few miles across and turn the sun into a black hole, nothing on Earth would change. Nothing at all. We would no longer have sunlight, of course. We would lose our warmth, our light, our gentle yellow companion in the daytime sky. But the Earth would not be pulled in. The Earth would continue to orbit, exactly as it does now, exactly at the same distance, with exactly the same year of 365 days around the new dark center of our solar system. The moon would still circle Earth. Jupiter would still drift quietly in its long, slow orbit. The whole gentle dance of the planets would continue undisturbed around a black hole instead of a star, as if nothing had happened at all. Because gravity does not care that the thing creating it is dark, or compressed, or strange. Gravity only cares about mass. And the mass of our sun, whether it is spread out into a glowing yellow ball 900,000 miles across, or compressed into a black hole only a few miles wide, is exactly the same mass. So the gravitational pull on Earth is exactly the same. The orbits do not change. The planets do not get sucked in. Life would end on Earth because of the lost light and warmth, of course, but not because the new black hole would devour us. From the gravitational perspective, nothing at all would change. I want you to feel how completely this overturns the popular image. There is no special pull from a black hole, no extra suction, no cosmic appetite. The gravitational reach of a black hole, at every distance beyond its surface, is exactly the same as the gravitational reach of any other object with that mass. Black holes only become unusual when you get extremely, extremely close to them. Closer than anything else in the universe will let you get to its center. Because most objects in the universe have a surface, and the black hole's surface is in a very strange place we will speak of later. But far away, far from that special inner region, a black hole is just another object with mass, gently tugging on its surroundings the way the sun does, the way Jupiter does, the way Earth tugs on you as you lie here in your bed. Nothing more. So if a black hole drifted by the outer edge of our solar system tonight, what would happen? Almost nothing. We might see, perhaps, some gravitational disturbance among the most distant comets, the soft outer halo of icy bodies that drifts in the great dark cloud surrounding our sun. But Earth would not be pulled in. We would not feel a thing. The black hole would be no more dangerous to us at that distance than any other dark wanderer of the night sky. This is the first piece of the false image we have to gently let go of. Black holes do not hunt. They do not chase. They do not have any special power to pull things in across vast distances. Like every other object in the universe with mass, they tug gently on their surroundings, and otherwise drift quietly through the dark, doing none of the dramatic things our stories have given them. They are, in this fundamental way, ordinary cosmic objects, and the extraordinary things about them happen elsewhere. Let us continue, gently, to find out what those extraordinary things really are. I want to dwell here a moment, because the false image of black holes as cosmic vacuums has shaped how we imagine these objects so thoroughly that it can take some time to set aside. In 1,000 science fiction stories, in countless dramatic documentaries, in the way we casually use the words black hole to mean any kind of devouring nothingness in everyday speech. The picture of the cosmic suction monster is woven into our culture. But it has no basis in physics. There is no special force coming out of a black hole that reaches across space to draw things in. There is only gravity. And gravity follows the same rules everywhere in the universe, whether the mass making the gravity is a star, a planet, a person, or a black hole. What this means, when you let it settle, is something quietly freeing. The black holes scattered through the cosmos are not threats to you. They cannot reach you across the dark and pull you toward them. They cannot grab Earth from billions of miles away. The supermassive black hole at the center of our own galaxy, 26,000 light-years from us, has no special power to disturb us here. It tugs on the sun, of course, the same way every other mass in the galaxy tugs on the sun. The whole galaxy, including our sun, is in a long, slow, gentle orbit around it. But that orbit is the same kind of orbit that the Earth has around the sun. A peaceful gravitational dance, nothing more. The black hole at the center of the galaxy does not threaten us. It does not even particularly notice us. We are simply one of 200 billion stars peacefully circling its quiet gravitational center, in the long, unhurried way that all things in galaxies do. There is a soft humility in this. The most feared object in the universe, when you actually examine it carefully, turns out to behave exactly the same way as every other massive object. Its gravity is ordinary. Its reach is ordinary. Only its density and the strange geometry near its event horizon are extraordinary. Everything else, from far away, is utterly normal. The cosmos does not have a single cosmic vacuum cleaner that hunts you across the dark. It has dense concentrations of matter that gently tug on their surroundings, the same way every other mass does, and otherwise drift quietly through space, asking nothing of the rest of us. The very word black hole carries within it a kind of misunderstanding so deep that it has shaped how we picture these objects for nearly a century. The word hole suggests an absence, an emptiness, a gap, a place where something used to be and now is not. A pit, a void, a tear in the fabric of existence. We picture them as something missing from the universe, a hole punched through space, leading nowhere, leading into nothing. But black holes are not holes. They are the opposite of holes. They are some of the most extraordinarily concentrated objects in all of existence. Concentrations of matter and energy so dense that they curve the very fabric of space around them in ways that are beautiful and strange and very far from being any kind of emptiness. Consider, when a star collapses to form a black hole, no matter has been removed from the universe. None has been destroyed. None has gone anywhere. Every single atom that made up the star, every proton, every neutron, every electron, every wisp of plasma and gas is still there. It has simply been compressed by the unimaginable inward pull of the dying star's own gravity into a region so small that we have not yet figured out exactly what happens at the very center of it. But the matter is there. The mass is there. The energy is there. None of it has become a whole. It has become something denser, more compact, more present than anything else in the universe. A black hole made from the collapse of a single massive star, what we call a stellar mass black hole, contains as much matter as several times our entire sun. Several whole suns packed into a region only a few miles across. The supermassive black holes at the centers of galaxies contain millions, sometimes billions of times the mass of our Sun, in regions still smaller than a single solar system. These are not holes. These are the most concentrated objects in the universe, and whole is exactly the wrong word for them. They are perhaps the fullest places in the cosmos, packed with matter and energy so tightly that the rules of how space and time work around them have to bend. So why do we call them holes? The name comes from how they look from the outside, not from what they are on the inside. From far away, a black hole appears, indeed, as a dark spot, a place from which no light escapes, surrounded by the glow of whatever is falling toward it. To early astronomers, this dark spot looked like a hole punched in the sky, like a window into nothingness, and the name stuck. But the darkness is not because nothing is there. The darkness is because the gravity of what is there is so strong that not even light can climb its way out once it has fallen close enough to the center. The blackness is not absence. The blackness is the silence of something so concentrated that even light cannot speak out of it. I find a soft wonder in this when I let it settle. We have lived for almost a century with a word, whole, that describes these objects backwards. They are not the absence of anything. They are an excess, a concentration, a gathering so intense that the universe itself bends around them. They are the densest, fullest, most present places in all of existence. To imagine a black hole correctly, you should not picture an empty pit. You should picture something so packed and so dense and so concentrated that even light, traveling at the fastest speed in the universe, cannot make its way out of the gentle but enormous pull of its gravity. And there is something almost tender about that when you think of it gently. The blackness of a black hole is not the blackness of nothing. It is the blackness of so much being present that no light can escape to tell us about it. The dark is not absence. The dark is fullness, gathered into a small place, holding itself in such tight stillness that even its own light cannot leave. There is more there, not less. More mass, more energy, more concentration than anywhere else in the cosmos. The word whole is wrong, but we will keep using it tonight because that is the name we have given them. Just remember, as we speak of them, that you are not picturing emptiness. You are picturing the opposite, the fullest, densest, most concentrated places in the universe, dressed up in the misleading clothing of a single, inaccurate word. If you would like a small thought experiment to help the truth of this settle, here is one. Imagine taking all the matter of the entire planet Earth, every ocean, every mountain, every cloud, every body, every grain of sand, and every bacterium, and compressing it inward, gently and patiently, until it occupied a region only about the size of a small marble, about 1 centimeter across. Imagine all of Earth, every atom of it, compressed into that small marble. That marble would be a black hole. It would have all the mass of Earth and exactly the gravitational reach of Earth at any distance further out than the marble itself. The moon, if you somehow kept it where it is, would continue to orbit that marble exactly the way it orbits Earth now. The marble is not an absence of Earth. The marble is Earth, compressed to its black hole form. Every continent, every river, every memory, every breath ever taken by anyone on the planet. All of it pressed into something the size of a small candy on the table beside you. That is what a black hole is. Not a hole, a concentration, a small place holding an enormous fullness. For black holes that come from the deaths of stars, stellar mass black holes, the marble of compressed matter is larger, a few miles across perhaps, holding the mass of 3 or 5 or 10 suns. For the supermassive black holes at the centers of galaxies, the dense central region is larger still, but always, always much smaller than what surrounds it. The size of a black hole, as we usually quote it, is the size of its event horizon, the boundary in space beyond which not even light escapes, not the size of the matter at its center. The matter at the center is even more concentrated still, packed into something the very heart of which we do not yet fully understand. What I want you to hold as we drift on through the night is this gentle correction. The blackness is not absence. The blackness is fullness compressed into smallness, gathered into a small region of space and holding itself there so tightly that even its own light cannot escape. There is more inside a black hole than there is in most regions of the universe. The word whole suggests less. The truth is more. The black holes of the cosmos are not gaps in the night. They are deeply, completely, abundantly full of matter and energy, simply gathered into smaller spaces than we are used to thinking about. The cosmos is more present, not more absent, in the places we call holes. Here is the third truth that may surprise you, and the one I find most quietly beautiful. Black holes are not dark. The black hole itself, the region from which no light escapes, is dark, yes. But the black holes we actually see in the universe, when astronomers point their telescopes at them, are surrounded by some of the brightest, most luminous, most spectacular displays of light anywhere in the cosmos. The light comes from what we call the accretion disk. When matter falls toward a black hole, gas drifting in from a nearby star, or dust from the galaxy around it, or the shredded remains of an unlucky asteroid, it does not simply fall straight in. The matter has motion, and because it has motion, it spirals around the black hole as it falls, the way water spirals down a drain. And as it spirals, the matter gets compressed and heated, and the friction of all the particles rubbing against each other in this great inward spiral heats them to temperatures that are almost unimaginable. Millions of degrees, tens of millions, hundreds of millions. And matter heated to those temperatures glows. It glows like nothing on Earth glows. The accretion disk around a feeding black hole emits light so intense that, for the most active examples, the disk alone can outshine an entire galaxy of hundreds of billions of stars combined. These are called quasars, the brightest single objects we have ever observed in the universe. And they are powered by supermassive black holes in the hearts of distant galaxies, slowly devouring the gas around them. The black hole at the center is dark, but the swirling disk of matter falling toward it is among the most brilliant things in the cosmos. There's a famous image that you may have seen, the first ever photograph of a black hole, captured a few years ago by a network of radio telescopes all across the Earth, working together as one giant eye. The image shows a black hole at the center of a distant galaxy called Messier 87. And what does the image show? A dark central region, yes, the famous black of the black hole. But surrounding that dark spot, an enormous, luminous orange ring of glowing matter. The ring is not the black hole itself. The ring is the accretion disk, the soft glow of all the matter spiraling inward, lit up to brilliant temperatures by the long, slow fall toward the center. The black hole is dark, but it is not alone. It is wrapped in light, crowned in light, wreathed in light. And there are jets, too, on the most active black holes. Narrow beams of glowing matter and radiation shooting out from the spinning poles of the black hole, like cosmic fountains pointing away from the dark center, sometimes stretching for hundreds of thousands of light years across the dark gulf between the galaxies. The jets are brighter than anything most galaxies contain. The black hole at their root is dark, but the jets themselves blaze across the cosmos like enormous, patient beacons, telling the universe that here, at this small, dark point, there is something extraordinary going on. Even the quieter black holes, the ones that are not actively feeding, are not truly dark in the way we usually mean. Around them, space itself is gently distorted. Light from distant stars behind them gets bent by their gravity, creating beautiful arcs and rings of starlight curving softly around the dark center. To observe such a black hole is to see, in a sense, the universe itself made visible, the gentle warping of space made luminous by the starlight that flows past. So when you picture a black hole tonight, do not picture a black void in empty space. Picture a small, dark spot surrounded by an enormous, luminous ring of hot, glowing matter, sometimes shooting out two great beams of light from its poles, with all the distant starlight behind it, gently curving and bending around it in soft arcs. The picture is not dark. The picture is luminous. The picture is one of the most extraordinary visual phenomena in the cosmos. The dark of the black hole is a small island of stillness in the middle of an enormous brilliance, not a void in the night, but a quiet center at the heart of a vast, soft light. This is what black holes really look like when we look at them. There is something I find particularly beautiful about that first photograph of a black hole, the one of Messier 87. It took the combined effort of telescopes scattered all across the surface of the Earth, working together as a single, planet-sized eye, observing for years, processing the data for years more, to finally produce a single image. The image shows a fuzzy orange ring around a small, dark center, the ring brighter on one side than the other because of the way the material is moving toward us on that side and away from us on the other, dimming and brightening the light. It is not a sharp image. It is gentle, soft, almost dreamlike. But what it shows is real. A small, dark spot at the heart of a distant galaxy, 55 million light-years away,
surrounded by the soft glow of matter falling toward it. The first time humans had ever seen, with their own eyes, the silhouette of a black hole against the surrounding light. A few years after that first image, the same network of telescopes captured the supermassive black hole at the center of our own Milky Way galaxy, Sagittarius A star, the one we spoke of earlier. And there too, the same pattern, a small dark spot at the center, surrounded by a soft, luminous ring of glowing matter. The black hole at the heart of our own galactic home, finally photographed, finally seen for what it is. Not a void in the dark, a small, dark spot, wreathed in a gentle ring of light. The galactic center, made visible for the first time in human history. I find this strangely moving. For all the history of human civilization, the center of our galaxy was an invisible place, known only through indirect calculation, through the way the stars near it moved, through the gentle pull of its gravity on everything around. We had imagined it for centuries. We had calculated its mass for decades. And then, in our own lifetimes, we finally saw it. A small, soft, luminous ring with a dark center in the direction of Sagittarius. The patient mother at the center of our galactic home, briefly captured by the patient attention of all the Earth's telescopes working together. A photograph that no human being could have taken alone. A photograph that required the whole planet, in a sense, to make.
So when you picture black holes tonight, do not picture them as dark voids. Picture them as small, dark spots at the centers of soft, luminous rings. The rings made of the patient, slow glow of all the matter falling gently inward. The rings shining with a light that took an act of planetary cooperation to finally photograph. The black holes of the universe are some of its most quietly luminous features. The black in their name is only a small, soft heart inside a much larger ring of light. Now I want to gently take apart one more piece of the popular story. The image of the black hole at the heart of a galaxy as a voracious destroyer, slowly devouring the galaxy from the inside out, consuming the stars one by one, growing larger and hungrier with each passing eon. The image is wrong. The truth is closer to the opposite. At the center of nearly every large galaxy in the universe, including our own Milky Way, there sits a supermassive black hole. These are the largest of all known black holes, with masses that range from millions to billions of times the mass of our Sun. The one at the center of our galaxy is called Sagittarius A star, and it has the mass of about 4 million suns, packed into a region the size of a small solar system. It is, by any measure, an enormous and powerful object. And what does it do, this enormous black hole at our galaxy's heart? Almost nothing. It sits quietly at the center of the Milky Way, gently pulling on the stars and gas around it with its gravity, as the entire galaxy slowly turns around it. It is not devouring stars. It is not growing rapidly. It is not threatening Earth or any other planet. It is, for an astronomical object, remarkably calm. Quieter, in fact, than most supermassive black holes elsewhere in the universe. It feeds occasionally, when a cloud of gas or an unlucky star drifts close enough. But most of the time, it is essentially dormant, doing the gentle work of holding the center of our galaxy together with its gravity. And here is the lovely turn. Without the supermassive black hole at the center, our galaxy might not exist as we know it. The black hole is not a destroyer of the galaxy. It is, in a quiet way, one of its anchors, the gravitational keystone around which the whole great spiral of 200 billion stars patiently turns. Some astronomers now believe that supermassive black holes and the galaxies that surround them grew up together, shaping each other across billions of years, with the black hole's quiet gravitational presence helping to organize and stabilize the surrounding stars and gas as the galaxy formed. The galaxies and the black holes seem, in a deep way, to belong together. They are not enemies. They are companions. And when a supermassive black hole does feed, when matter does fall in, the energy released by the spiraling accretion disk pushes outward on the surrounding gas, slowing star formation in the inner galaxy, regulating the growth of the galaxy itself. It is a kind of gentle thermostat. When the black hole feeds, it releases energy that limits how much more matter can fall in, and how rapidly the galaxy can change. It is not eating the galaxy. It is, in a slow, patient way, helping to keep it in balance. I find this almost beautiful. The thing we have feared most at the center of every galaxy, the great, hungry monster waiting in the heart, is, when we actually look at it, more like a quiet gravitational mother, holding the galaxy together with her gentle pull, regulating the flow of matter, helping to make the whole structure stable enough for stars to form, and worlds to gather, and life to slowly arise. The center of the Milky Way is not a wound. It is an anchor, a hearth, a quiet center around which everything we love can patiently turn. And here is what is most moving to me. The supermassive black hole at the center of our galaxy has been there, doing this gentle work of holding things together for billions of years, far longer than the Earth has existed. It has been our quiet companion, the deep gravitational center of the great spiral home we live in, since long before there were any beings on this small blue world to look up and wonder about it. It has not threatened us. It has, in a real sense, made the very possibility of us. Without something like it at the center of our galaxy, the matter that would become Earth might never have gathered. The sun might never have formed. The slow, patient assembly of everything we love might never have happened. The black hole at the heart of the Milky Way is not the enemy of life. It may be one of its silent founders.
There is a phrase astronomers sometimes use when they talk about the relationship between supermassive black holes and the galaxies that surround them. They call it co-evolution. The black hole and the galaxy grew up together. They are not strangers who happen to occupy the same space. They are deeply intertwined, shaped by the same long history, each influencing the other across billions of years. The mass of a galaxy's central black hole is closely related to the mass of the stars in the galaxy's central bulge, in a way that suggests a deep gravitational and energetic conversation between the two over the entire history of the galaxy. They are partners in the cosmic dance. They are family. When you look at the night sky and see the soft band of the Milky Way arching across the dark, you are looking at a galaxy whose entire shape and structure has been quietly shaped, in part, by the gentle gravitational presence of the supermassive black hole at its center. The spiral arms, the central bulge, the slow turning of 200 billion stars, all of it has been organized over billions of years by the combined gravity of all the matter in the galaxy, with the central black hole as one of its most important contributors. Without it, the Milky Way would be a different galaxy, possibly not a galaxy that could give rise to worlds like ours. And I want you to feel the gentleness of this. The black hole at the center of our galaxy is not just neutral toward life. It may, in a quiet way, be one of its preconditions. The dark center is not the enemy of the light that scatters through the galaxy around it. The dark center is part of what makes that light possible. Galaxies and black holes belong together. They have grown together. They have shaped each other. They will keep doing so, gently, for the rest of cosmic time. Let us approach one now, gently, in our minds, and see what really happens as you draw close to a black hole. Because here again, the popular image is misleading. We have been told that approaching a black hole is a violent and terrifying ordeal, that you would be stretched and torn apart in unimaginable ways the moment you got near. But the truth, as so often with black holes, depends entirely on which black hole and how big it is. The outer edge of a black hole, the boundary beyond which not even light can escape, has a special name. It is called the event horizon. Think of it as a kind of invisible spherical boundary in space, centered on the black hole. Anything outside the event horizon can, in principle, still escape, can still climb back out against the pull of the black hole's gravity if it is moving fast enough. Anything that falls inside the event horizon cannot. Once you are inside, you cannot return. Not because you are physically held there by some force, but because all the possible paths through space and time from inside the horizon lead inward, not outward. We will come back to this strangeness in a moment. The event horizon is not a wall, not a surface you would feel as you crossed it. It is not made of anything. It is simply a region of space marked by a particular geometric property, the place beyond which, if you keep going, you cannot turn back. For a stellar mass black hole, made from the collapse of a single dying star, the event horizon is small, perhaps a few miles across. For a supermassive black hole at the center of a galaxy, the event horizon can be enormous, millions or even billions of miles in radius. The horizon scales with the mass. And here is where the popular image becomes especially wrong. For a small black hole, a stellar mass black hole, just a few miles across, the gravity changes so quickly with distance that as you fell in, your feet would be pulled much harder than your head, and you would be stretched, painfully and lethally, into a long, thin filament long before you ever reached the horizon. Astronomers have a word for this. They call it spaghettification. For small black holes, it is real, and it is exactly as unpleasant as it sounds. But here is the lovely truth. For the largest black holes, the supermassive ones at the centers of galaxies, The geometry is utterly different. The event horizon of a supermassive black hole is so far from the central concentration of mass that the gravity changes very, very slowly with distance. You could cross the event horizon of a supermassive black hole, in principle, and feel almost nothing at all. No stretching, no tearing, no spaghettification. The horizon would be, from your local perspective, a perfectly ordinary place in space. The gravity would be enormous, yes, but smooth and gentle, with almost no difference between what your head feels and what your feet feel. You could drift across it the way a leaf drifts across a stream, barely sensing the crossing at all.
There is something I find almost unbearably tender about this. The boundary that we have been told is the most violent place in the cosmos, the edge of the black hole, is, for the largest of them, a perfectly calm place. A place where nothing locally remarkable seems to happen at all. The crossing is invisible. You would not know you had crossed. You would simply find yourself, suddenly, in a region of space from which you could not return. But the crossing itself, the moment of stepping through, would feel like nothing more than a soft moment of drifting onward through the dark, with no particular sign that anything had changed at all. The largest event horizons in the universe are, in a strange way, among the most peaceful surfaces in existence. They are smooth, they are quiet, they produce no fanfare as you cross them. You simply drift, gently, into a new region of the cosmos from which there is no path back. Not because anything dramatic happens at the crossing, but because all the paths from where you now are lead onward, inward, toward the center, never outward, never back. The drama of the black hole is not at its edge. The drama, if there is any, is deep inside. I want to dwell here for a soft moment more, because I find this particular truth so far from the popular picture that it deserves the time. The event horizon of a supermassive black hole, the largest such horizon you can find in the universe, is not a violent place. It is one of the calmest surfaces in existence. It is a sphere in space, smooth and featureless, marked by no boundary that any local instrument could detect. If you drifted through it slowly enough, on a long, quiet trajectory, you would notice nothing at the moment of crossing. The stars behind you would still be visible, gently dimming as their light slowly stretched and dimmed in the gravitational field. The stars ahead of you would still be there. The cosmos around you would not change in any abrupt way. You would simply find yourself, gradually, in a region from which there was no return. But the gradual entering of that region would be one of the most peaceful experiences imaginable. This is so different from the popular image that it can take some time to settle. We have been told the event horizon is a wall of unimaginable violence. The truth is that, for the largest black holes, it is almost a kind of soft veil, a boundary in space whose existence you would not even notice as you crossed it. The horizon is, locally, ordinary. The geometry around it is curved, yes, in ways that ultimately make it a one-way membrane. But the curvature is gentle. The local experience is smooth. The crossing is quiet. What you would notice, if you were the falling observer, would be the strange way the universe behind you looked as you fell. The light from outside would gradually shift toward the red end of the spectrum, growing slower and redder as you fell deeper. The whole cosmos behind you would seem to slow down, as if the rest of the universe were patiently fading away into a soft red dim. But there would be no jolt,
No sudden tearing, no wall of fire. Just the slow, gentle dimming of everything behind you. The slow, gentle reddening of all the stars you used to know. The quiet replacement of the cosmos you came from by the new, strange interior of the place you have entered. For the largest black holes, the experience would be more like a slow, soft fade than a violent crossing. The cosmos behind you would gradually disappear into a gentle redshift, while you yourself would simply continue peacefully on toward whatever lies inside. I find something quietly tender in this. The most extreme boundary in the universe, the edge of the black hole, is, for the largest of them, not a violent place at all. The largest such boundaries in the cosmos are gentle, smooth, almost ordinary. They produce no fanfare. They demand nothing of the falling observer. They simply mark the soft transition between one region of the cosmos and another. The horizon is, for the largest black holes, perhaps one of the gentlest surfaces in all of existence. And then, only after that gentle crossing, the strange interior begins. Now we come to perhaps the strangest and most beautiful piece of the truth about black holes. Because what happens once you have crossed the event horizon, once you are inside the black hole, is something so different from what happens anywhere else in the universe that physicists have struggled to describe it for nearly a century. It is not a place. It is, in a deep sense, a different kind of geometry, in which the very ideas of space and time soften and rearrange themselves.
Outside a black hole, time always flows in one direction. It is the one direction you cannot avoid, the one direction you cannot turn around in. You can move forward or back in space, left or right, up or down, but you cannot move backward in time. The future is always ahead, the past always behind, and you can no more refuse the arrival of tomorrow than you can refuse the law of gravity. Time is the inevitable direction. Inside the event horizon of a black hole, something extraordinary happens. The mathematics of general relativity, Einstein's theory of how space and time work in the presence of gravity, tells us that, inside the horizon, the role of time and one direction of space switch. The center of the black hole, the singularity that lies somewhere at its heart, becomes not a place, but a time, a moment, a future. And the inward direction, which on the way in seemed like a direction in space, becomes the direction of the future itself, the one direction in which you cannot help but move. This is hard to picture, and it is harder still to feel. But let me try. Outside the horizon, down, the inward direction toward the black hole, is a direction in space. You can choose to go down, or to refuse, or to turn around. Inside the horizon, down stops being a direction in space and becomes the direction of time itself. The center of the black hole is no longer somewhere. It is somewhen. It is the future. And just as you cannot avoid tomorrow, no matter how you turn or how you struggle, you cannot avoid the center of the black hole once you have crossed the horizon. Every direction you could possibly travel, every choice you could possibly make, every motion you could possibly attempt, leads you, inexorably, toward the center. Not because something is pulling you, because the center has become your future. And the future is the one thing in the universe that always arrives, no matter what. I find this one of the most quietly beautiful pieces of physics I have ever learned. The strangeness of a black hole is not that it pulls you in. The strangeness is that once you are inside, inward stops meaning in space and starts meaning in time. You do not fall into a black hole the way you fall into a hole on Earth. You fall into the future. The center of the black hole becomes the next moment, and the next, and the next, and you cannot help but go on toward it, the same way you cannot help but go on toward tomorrow, no matter how slowly or how carefully you breathe. And there is something almost tender in that, somehow. The thing we have feared most, being trapped at the center of a black hole, turns out to be, in the deepest mathematical sense, the same kind of trapping that holds us all in time. We are all moving, inexorably, toward the next moment. We cannot stop. We cannot turn around. The future always comes, and we always go to meet it. Inside a black hole, the geometry is simply more honest about this. The center is the future, and you are moving toward it, the way you are moving toward your own next breath, the way the whole world is moving toward its own next day. In this sense, falling into a black hole is just a slightly more dramatic version of what every conscious being is already doing, every moment, all the time. You are falling, gently, into the future. You always have been. The black hole only makes the geometry of it visible in a particularly stark and beautiful way. And there is more strangeness still, deeper than this. The interior of a black hole is not just a place where time and space have swapped roles. It is a place where the very ideas of distance, direction, and duration become slippery in ways that physicists are still working out. Einstein's equations describe what happens up to a certain point, what happens close to, but not quite at the very center, the singularity. At the singularity itself, the equations of general relativity break down. They give answers that involve infinities, and infinities in physics usually mean that the theory is no longer a complete description of what is happening. We do not actually know what is at the very center of a black hole. We do not know what the singularity really is. We have mathematical descriptions of the geometry around it, but the very center remains one of the great open questions of modern physics.
Most physicists believe that quantum effects, which become important on extremely small scales, take over near the center, replacing the classical singularity with something quantum mechanical, something we do not yet have the right theory to describe. The unification of general relativity with quantum mechanics, which would tell us what the center of a black hole really is one of the great unsolved problems of physics. There are candidate theories, string theory, loop quantum gravity, others, but no consensus on which, if any, is correct. The center of a black hole, in this sense, is one of the few places in the universe where our most successful theories of physics simply do not work. Whatever is at the heart of a black hole is something we have not yet figured out. I find this almost lovely in a quiet way. The most extreme places in the universe, the centers of black holes, are also some of the places we know least about. They are the frontier of physics, the soft edge of human understanding, the places where our equations gently fail and we are left wondering. The cosmos has not yet given us all of its secrets. Even at its strangest points, it still holds surprises that the next generations of physicists will, perhaps, eventually understand. So, when you picture the inside of a black hole tonight, do not picture a known thing. Picture a region where time and space have softly traded places, where the center has become the future rather than a location, and where, at the very heart, our best theories of physics gently break down, and we admit that we do not yet know. The interior of a black hole is one of the great honest mysteries of the universe. We have many beautiful partial answers, and one very large open question at the center.
and the honest acknowledgement of what we do not know is itself one of the gentler features of the science we are slowly building together. Let me now come back to the gentle, quiet, supermassive black hole at the center of our own galaxy, because I want to dwell on it with the care it deserves. Her name is Sagittarius A star, pronounced Sagittarius A star, and she is one of the most important presences in our cosmic home, and almost certainly one of the gentlest objects of her size in the entire universe. She lies about 26,000 light-years from Earth in the direction of the constellation Sagittarius. If you go outside tonight and find that constellation, it looks, depending on your part of the world, like a teapot drawn in soft stars. And if you look toward its handle, you are looking toward the center of our galaxy, and you are looking, more or less, toward her. The light you see in that direction left long before any of us were born. The black hole at the center of our galaxy is so far away that her light, if she had any to give, would take 26,000 years to reach us. She has the mass of about 4 million suns. That sounds enormous, and it is. But on the scale of supermassive black holes elsewhere in the universe, she is actually modest. The largest supermassive black holes known have masses of tens of billions of suns. Sagittarius A star, our own galactic center, is comparatively small. And she is also, by the standards of supermassive black holes, remarkably calm. She is not actively feeding. There is no bright accretion disk around her, no roaring jets, no quasar-bright burst of energy from her vicinity. She is, by cosmic standards, dormant, a quiet center drifting through her long, patient, gentle eon at the heart of the galaxy. But she is not idle. She is doing the gentle gravitational work of being the central anchor of the Milky Way. Around her, every star in the galaxy traces out its long, slow orbit. Our own Sun, and Earth along with it, has been making one slow circuit around Sagittarius A star for billions of years, taking about 225 million years to complete a single galactic orbit. That is so long that since the dinosaurs walked on Earth, we have completed about 1/3 of one orbit. The slow turning of the Milky Way around this gentle, dark center is one of the longest and quietest motions in all of nature. And here is what I find moving. Sagittarius A star has been there, holding the center of our galaxy together for so long that she predates the Earth itself. She predates the Sun. She predates everything we love. She is older than the elements of which our bodies are made, older than the carbon in your blood, older than the iron in your hemoglobin, older than the calcium in your bones. The gentle gravitational center of our galactic home has been quietly holding everything together in her long, patient way since long before there was anyone here to be held.
And she will continue. Long after our sun has burned out, long after the Earth is gone, long after every human story has come and gone, she will still be there, at the center of what remains of the Milky Way, drifting in her gentle eon, holding whatever stars are left in their long, slow orbits around her. She is one of the most patient, most enduring, most gentle features of our cosmic home. She is not a monster. She is the dark heart of the galaxy we live in. And dark here means not absent, but full. Full of mass, full of patience, full
of the slow gravitational love that has held our whole galactic home together since before we were here, and will hold it long after we are gone. If you are finding some peace in this slow drift through the truth of black holes, and you would like more of these quiet journeys to find you on other nights, you might take a soft moment to subscribe. It is the simplest way to let the next one come to you, the next time you need a place of quiet to rest. Then let the thought go and return to the gentle dark and to the patient mother at the center of our galaxy. I want to share with you, gently, one more thing about Sagittarius A star that I find quietly moving. Astronomers have been able to track with very long observations using telescopes that can see in the infrared the orbits of individual stars that pass very close to her. These stars, called the S stars, swing around her in long elliptical orbits, some of them coming within a few light hours of the event horizon at their closest approach. The most famous of them, called S2, completes a full orbit around Sagittarius A star in about 16 years, swinging out far from her and then plunging back in toward her at speeds of nearly 2.5% the speed of light at closest approach. Astronomers have watched for decades now as these stars trace out their patient orbits around the gentle gravitational center of our galaxy. The orbits exactly match what Einstein's theory of general relativity predicts. Every observation, every passage, every careful measurement of the stars near her, all of it confirms that she is exactly what we believe her to be. A supermassive black hole, 4 million times the mass of our Sun, drifting quietly at the center of the galaxy, holding everything in place with her gentle, patient gravity. And the stars closest to her have been doing this dance, swinging close, slowly fading away, swinging close again, for as long as they have existed. Some of them probably formed nearby, in regions of space that we cannot easily understand, somehow able to coalesce despite the strong tidal forces of the central black hole. Others may have drifted in from further out, captured into their close orbits by gravitational encounters with other stars. They are dancers, in a sense, long-lived dancers, swinging in great long ellipses around the quiet center, century after century, millennium after millennium, in a dance that has been going on for far longer than human history and will go on for far longer than human history will last. I find it moving to think of this dance happening right now, 26,000 light years from us, in the direction of Sagittarius. The S stars swinging around her quietly, the gas drifting in occasionally to brighten her temporarily before settling back to dim. The hundreds of billions of more distant stars all turning slowly around the galaxy as a whole. The whole great spiral motion of the Milky Way, anchored by the patient, quiet center. the gentle mother in the middle, who has been doing this work for billions of years, and asks nothing of us but our occasional, respectful wonder. Tonight, somewhere in the direction of the constellation Sagittarius, the dance is still going on. The stars are still swinging close to her and out again. The matter is still occasionally drifting in. The galaxy is still slowly turning. And she is still there, patient and quiet, holding it all together, asking nothing, drifting in her long eon of gentle gravitational work. She has been there since long before us. She will be there long after us. And tonight, while you rest, she is still doing exactly what she has always done, with the same patient calm. This is the gentle mother at the center of our galactic home.
There is something that black holes do when they meet each other that is one of the most extraordinary phenomena in all of physics, and one of the most quietly beautiful things humans have ever managed to detect. They embrace. Two black holes drifting slowly toward each other over enormous spans of time spiral inward through the dark, slowly closer and slowly closer, until at last they touch and merge and become a single, larger black hole. And in the moment of their meeting, they release a soft ringing in the very fabric of space itself, a kind of music that spreads outward through the cosmos at the speed of light, traveling across the universe to reach us. We call these ripples gravitational waves. They were predicted by Einstein more than 100 years ago, a consequence of his theory of how gravity works. He calculated that anything that has mass and accelerates should produce small ripples in the fabric of space and time around it. For most things, these ripples are unimaginably small, far below anything we could ever detect. But for the most violent events in the universe, and the merging of two black holes is one of the most violent, the ripples could be just barely large enough that, with enough patience and enough technology, we might one day catch them. For decades, this was just a beautiful theoretical prediction. No one had ever observed a gravitational wave. The instruments needed to detect one were so sensitive that they would have to measure changes in length smaller than 1,000th the width of an atomic nucleus, over the 4 kilometers of a laboratory built specifically for this purpose. It seemed almost impossible to achieve. But patient teams of physicists and engineers, working for decades, slowly built such instruments. They called them LIGO, the Laser Interferometer Gravitational Wave Observatory. And in September of 2015, the first gravitational wave was finally detected. What had happened to make the wave that we caught? Far away, more than 1 billion light-years from Earth, 2 black holes had been spiraling toward each other for an unimaginably long time, drawn slowly together by their mutual gravity. As they spiraled, they radiated energy into the very fabric of space around them, gradually losing the orbital energy that kept them apart, gradually drawing closer and closer. Eventually, after billions of years of slow approach, they reached their final in-spiral, the last seconds of their long journey toward each other, and they began to spin around each other at unimaginable speeds, faster and faster, their event horizons drawing together in a final, intimate dance. And then, in a fraction of a second, they merged. Two black holes became one, and the ripple of their merging spread outward across the universe. For more than 1 billion years, that ripple traveled. It crossed the great empty spaces between galaxies. It passed by stars and worlds and the rare flickers of life that may exist in the cosmos. And finally, on a quiet day in September of 2015, it reached our small blue world, and it gently stretched and squeezed the careful laser beams of the LIGO detectors by a tiny, tiny amount. And we caught it. We caught the soft echo of two black holes embracing each other, 1 billion years ago, in some unimaginably distant corner of the cosmos. When the engineers translated the wave into sound, slowing it down so we could hear it within the range of human ears, what came out was a soft chirp. A single rising tone, lasting only a fraction of a second, rising in pitch as the two black holes spiraled faster and faster, and then ending abruptly as they merged into one. It is one of the gentlest, most musical sounds in all of nature. The chirp of two black holes meeting each other after 1 billion years of slow approach. A single note, a soft cosmic song. Since that first detection, we have caught dozens more. Black holes, all over the universe, have been finding each other for billions of years, embracing in their slow, patient way, and sending out soft musical ripples that we are only now learning to hear. The cosmos, it turns out, has been quietly singing with these soft notes for as long as it has existed. And we have, finally, learned to listen. The universe is more musical than we ever knew, and the black holes, those things we feared most, are the ones making some of its softest, most beautiful songs.
There is something so gentle about this discovery that I find it hard to convey. Before September of 2015, no human being had ever felt a gravitational wave, ever observed one, ever known with direct evidence that they existed. They were a mathematical prediction from a 100-year-old theory, beautiful but invisible, calculated but never seen. And then, one quiet day, a ripple from 1 billion years ago finally reached our small blue world. And the careful instruments we had built to detect such ripples picked it up. And in that moment, the universe became newly audible. A whole new sense had been added to humanity's perception of the cosmos. We had been listening to the universe in light for thousands of years. Suddenly, we could listen in gravitational waves too. A second sense. A second way of perceiving the cosmos. A second song. And the song the universe has been singing in gravitational waves turns out to be a soft song of black holes finding each other. Most of the gravitational waves we have detected come from black hole mergers. The cosmic chirp, repeated over and over, in different keys and at different volumes, from different distances and different masses, all telling the same story. That black holes have been drifting toward each other across the dark for billions of years, embracing each other in slow, patient gravitational dances, and ringing the universe gently as they meet. This is the music of the cosmos that we are only now learning to hear. And it is, beautifully, made by the very objects we used to fear the most. I think about this sometimes when I am lying awake at night. Somewhere out in the dark, right now, two black holes are slowly drifting toward each other. They have been doing this for hundreds of millions of years. They will continue to do it for many more. They are still far apart, separated by enormous spans of dark space. But they are drifting, slowly, toward each other, drawn by the patient gravity that connects them, in a dance that will end someday in a soft cosmic chirp. And we, by then, may be long gone. Or we may still be here, with instruments more sensitive than LIGO, listening as those two black holes finally meet and sing their soft note to the cosmos. Either way, the dance is happening. The slow approach, the patient gravitational pull, the eventual gentle meeting. The universe is full of such dances, going on right now in the dark. We have learned to hear only the soft music they make when they end. But the dances themselves, the patient, long, slow approaches, are happening everywhere, all the time. In the dark spaces between the galaxies and within the galaxies themselves. The cosmos is, in this way, a very romantic place. Black holes are finding each other, slowly, all the time. And when they meet, the universe rings, softly, with the sound of their meeting. There was a physicist named Stephen Hawking who lived from the middle of the 20th century into the early 21st, and who spent much of his life thinking about black holes. He was a man who endured a great deal, diagnosed in his 20s with a slow, degenerative illness that gradually took away nearly all of his ability to move, leaving him in a wheelchair for most of his life, eventually requiring him to speak through a computer-generated voice. And yet, in that body, he kept thinking. He kept patiently exploring the strange mathematics of black holes, with the gentle determination of someone who knew that the deepest mysteries are reached slowly and with quiet attention. And in the middle of the 1970s, he discovered something about black holes that astonished the world. He discovered that they are not eternal, that they do not, in fact, last forever, that every black hole in the universe, even the largest supermassive black holes at the centers of galaxies, even the smallest stellar mass black holes, is slowly, slowly, slowly evaporating. How can this be? Black holes, after all, do not let anything escape. Their event horizons are, by definition, one-way membranes. Once something falls in, it cannot come back out. So how can a black hole shrink? How can it lose mass?
Hawking found the answer in the strange place where two great pieces of physics meet. General relativity, which describes how gravity bends space and time on large scales, and quantum mechanics, which describes how things behave on the smallest scales. He discovered that, very near the event horizon of a black hole, quantum effects in the vacuum of space itself cause something subtle and beautiful to happen. Pairs of virtual particles, constantly flickering in and out of existence in empty space, a kind of soft quantum dance that is happening everywhere in the universe all the time, sometimes get separated by the event horizon. One falls in, the other escapes. And the one that escapes carries away a tiny amount of energy from the black hole, in the form of what we now call Hawking radiation. This radiation is incredibly faint. For a stellar mass black hole, the rate of evaporation is so slow that it would take vastly longer than the current age of the universe for the black hole to lose any noticeable mass at all. For a supermassive black hole, the rate is even slower, orders of magnitude slower still. So slow that the supermassive black holes will outlast almost everything else in the universe, evaporating only on timescales of unimaginable length. But they will evaporate. Slowly, patiently, across spans of time so vast they exceed the current age of the universe by astronomically incomprehensible factors. The largest supermassive black holes may take 10 to the 100th power years to fully evaporate. That number, 10 to the 100th power, has no name in any human language. It is so much larger than the current age of the universe that comparing them is almost meaningless. But it is not infinite. The evaporation is real. The black holes will, eventually, give back everything they have ever taken. I find this almost unbearably beautiful, in a way I find hard to describe. The thing we have feared as the most permanent, most absolute prison in the universe, the place from which nothing ever returns, turns out, on long enough timescales, to be patient and gentle, and ultimately willing to release everything it has gathered. Black holes are not eternal. They are temporary on the largest possible scale, but temporary nonetheless. They gather matter and energy for an unimaginable span, and then, slowly, gently, across spans of time too vast to picture, they give it all back. The cosmos itself, in its deepest mathematics, refuses to let anything be truly lost forever. Even what falls into a black hole, in the end, comes back out, transformed into the soft drift of Hawking radiation, returning to the great quiet of the universe. Stephen Hawking discovered this, sitting quietly in his wheelchair, thinking patiently for years about how the equations should fit together. He gave us back, through pure thought, the gentle assurance that the universe does not have permanent prisons. Everything that the cosmos gathers, the cosmos eventually returns. It just sometimes takes a very, very, very long time. There is a kind of quiet patience in this that I find moving. Stephen Hawking lived for many years with a body that gradually stopped responding to him, with senses that gradually gave way, with a voice that eventually had to be replaced by a computer-generated approximation. And yet, in that increasingly quiet body, his mind kept patiently working out the gentle equations of the universe. He kept asking small, careful questions about what happens at the edge of a black hole, about what quantum mechanics has to say about Einstein's equations, about whether the universe might be more generous than we had thought. And he found that it was. He found that even the most absolute-seeming prisons in the cosmos are, in the end, gentle and patient, and willing to release everything they hold. He gave humanity a piece of soft, good news from the deepest mathematics of the universe, in the same years that his own body was, in its own way, failing around him. There is something almost prayerful about that.
The patience of Hawking radiation, when you really sit with it, is one of the most generous patiences in nature. A supermassive black hole of 1 billion solar masses might take 10 to the 100th power years to fully evaporate. Let me try to give you a sense of that number. The current age of the universe is about 13.8 billion years. That is, about 10 to the 10 years. 100th power year is a 1 followed by 100 zeros. The ratio between the evaporation time of a large supermassive black hole and the current age of the universe is, then, about 10 to the 90th power, a 1 followed by 90 zeros. The patience required is essentially incomprehensible, but it is finite. The patience eventually ends. The black hole eventually returns its contents to the universe. The cosmos is patient, but it is not actually permanent. Everything, in the very long run, comes back. I find this softens something in me when I let it. I have always struggled, in my own quiet way, with the idea of permanent loss. The thought that something can simply be gone, gone forever, gone in a way that nothing can ever undo, it has a heavy weight to it. But the deep mathematics of the universe, as Hawking discovered, does not really seem to support that kind of permanent goneness. The cosmos, at its deepest level, prefers to return things rather than to keep them. The most absolute prisons in the universe are, in the end, temporary. The patient evaporation gives everything back. There is no permanent prison in the cosmos. Nothing is ultimately kept. Everything, on long enough timescales, is gently returned. I do not know what to make of this in any larger sense. I am not a theologian or a philosopher, but as a small piece of physics, it brings me a quiet comfort. The universe is built, at its deepest level, to give things back. Even the things that seem most lost. Even what falls into a black hole. Even, in the very, very long run, everything we have ever feared we might never see again. The cosmos is patient. The cosmos is generous. The cosmos eventually returns what it gathers. We just sometimes have to be patient with it. And the patience required, for the largest things, is sometimes greater than any being could possibly endure. But the return is real. The return is built into the very equations of physics. The return, eventually, comes. Stephen Hawking gave us this. Sitting quietly in his chair, thinking patiently, year after year. A small, soft assurance from the deepest mathematics of the universe that nothing is ever truly lost. There is a deeper layer to what Stephen Hawking discovered, and it has occupied physicists ever since. It is called the black hole information paradox, and it touches on something that I find quietly moving. The question of whether anything that falls into a black hole is truly lost, or whether everything is somehow remembered, somehow preserved, somehow whispered back out into the cosmos at the end. Here is the puzzle, as gently as I can put it. In ordinary physics, everywhere else in the universe, information is conserved. The state of any system at any moment, if you knew every single detail of it, could, in principle, be used to reconstruct what came before. Burn a book, and the information in the book seems to be gone. But in principle, if you could track every single atom and photon released by the burning, every drift of smoke, every flicker of heat, you could reconstruct the book. Information, in the deepest sense, is never truly lost. It is just rearranged into forms that make it impossibly difficult to read. But if a book falls into a black hole, and the black hole then slowly evaporates over an unimaginable span of time, what happens to the information about the book? If the black hole simply gives off plain, featureless Hawking radiation, as Hawking originally calculated, then the information about the book seems to be lost. Gone. Erased from the cosmos in a way that no other physical process does. This violated something deep that physicists hold dear, and it created a problem that physicists have been quietly working on for decades.
The puzzle has gradually softened, in recent years, into something more beautiful. Many physicists now believe that the information is not, in fact, lost. That somehow, encoded in subtle correlations between the photons of Hawking radiation that gently drift out from the black hole over the eons, the full information about everything that ever fell in is preserved. The Hawking radiation is not as featureless as it first appears. It is perhaps a slow, patient encoding of everything the black hole ever swallowed, released back to the cosmos, one tiny photon at a time, across spans of time so long that no being in the universe could ever assemble the pieces. But in principle, the information is there,
The book is not lost. It has only been shredded into the softest possible whisper, dispersed across the entire history of the universe, returned drop by drop to the great, patient quiet. There is a related idea called the holographic principle that I want to mention, because it is one of the most beautiful pieces of modern physics. It suggests that everything that ever falls into a black hole is somehow encoded on its event horizon, the two-dimensional spherical surface that marks the boundary of the black hole. The interior of the black hole in this picture is not where the information lives. The information lives on the surface, like the way a hologram encodes a three-dimensional image on a two-dimensional sheet. Everything that fell in is, in some deep sense, still there, but stored on the boundary, not lost in the depths. I find these ideas deeply consoling. The thing we have feared as the great place of cosmic erasure, the black hole, may, in the end, be one of the most faithful preservers of information in the universe. Nothing that falls in is truly lost. The book, the star, the planet, the wandering bit of matter, all of it is somehow remembered, somehow stored, somehow whispered back out into the universe across the long, patient eons. The cosmos does not erase. It only takes a very long time to give things back. And there is something tender in that, too, that reaches beyond physics. The deepest mathematics of the universe seems to want nothing to be permanently lost. Everything is remembered, somewhere, somehow, even by the things we thought most likely to forget. The patient memory of the cosmos is longer and gentler than we knew. And the black holes, far from being the great forgetters, may be among the most faithful rememberers of all. I want to spend a soft moment more on the holographic principle, because it is one of the strangest and most beautiful ideas in modern physics, and one that has changed how I think about the universe in subtle but real ways. The basic idea, again, is that the information about everything that falls into a black hole is somehow stored on its event horizon, on the two-dimensional spherical boundary that marks the edge of the black hole, rather than lost in the depths of the interior. The interior, in this view, is, in some sense, a kind of mathematical illusion. The real information lives on the boundary. The deeper implication of this idea, which has been explored by physicists over the last several decades, is that perhaps the same thing is true of the entire universe. Perhaps everything we experience as a three-dimensional cosmos, every star, every galaxy, every world, every breath you have ever taken, is, in some deep mathematical sense, encoded on a two-dimensional boundary that surrounds the universe. The cosmos we inhabit in this picture is a kind of holographic projection from a more fundamental boundary description. The universe is a hologram. We are part of a hologram. The three-dimensional richness we experience is, in some deep way, encoded in a two-dimensional surface that we cannot see. I do not know if this is true. The holographic principle is a beautiful conjecture, with some compelling mathematical evidence supporting it in particular contexts, but it has not been proven for the universe at large. It is one of the leading candidates for a unified theory of physics, but it is not yet established. Still, the very fact that the deepest mathematics of black holes might suggest such a picture about the entire universe is one of the most extraordinary turns in modern physics. Black holes, those things we used to fear, may be telling us something profound about the nature of reality itself. That everything we see, everything we love, everything that exists, may be encoded in a surface we cannot see, projected outward into the three-dimensional experience we know.
And the gentleness of this idea, when you let it settle, is striking. Nothing is lost, because everything is encoded on a boundary that holds it all. The universe, in this picture, is a vast act of patient remembering. Every star, every world, every soft moment, all encoded somewhere on a boundary that we cannot directly see, but that holds the full information of everything. The cosmos remembers itself in this deep way. Nothing falls out of the universe's memory. Everything is preserved, somehow, somewhere, in the deep structure of reality. Black holes, in this view, are not exceptions. They are simply small versions of what the entire universe is doing, encoding all of their information on their boundaries, holding it patiently, releasing it slowly. Every black hole is a small model of the cosmos itself. Every black hole is a small example of the universe's deep tendency to remember rather than to forget. Every black hole is a tiny, patient archive, holding within its surface the soft history of everything that has ever crossed its horizon. And the universe at large, perhaps, is the same kind of archive, on the largest possible scale. A great, patient memory, holding everything, forgetting nothing, gently keeping the soft history of everything that has ever happened. I find this almost unbearably consoling. The universe, in its deepest mathematics, seems to want to remember. Black holes are not exceptions to this. They are gentle reminders of it. They are small versions of what the cosmos itself, perhaps, is doing on the largest possible scale. Up until now, we have been speaking of the great black holes of the cosmos, the stellar mass ones, made from the deaths of large stars, and the supermassive ones, sitting at the centers of galaxies. But there is another kind of black hole, predicted by physics, that we have not yet found in the universe, but that may exist. The smallest possible black holes, the ones that are smaller than a single atom. These are called primordial black holes, and they would have been formed not by the collapse of stars, but by tiny, tiny imperfections in the first moments of the universe itself. In the chaos of the early cosmos, certain small regions may have been compressed so tightly by the surrounding pressure that they collapsed into miniature black holes, far smaller than anything we usually think of when we hear the words black hole. Some would have been the mass of a small mountain, but compressed into a region smaller than a single atom. Others would have been less massive still, black holes the mass of an asteroid, or even just a single building, but still so dense that their event horizons were microscopic. And here is the lovely turn, courtesy again of Stephen Hawking's discovery. The smaller a black hole is, the faster it evaporates. The supermassive ones take 10 to the 100th power years to evaporate. The stellar mass ones take 10 to the 67th or so. But the tiny primordial black holes, the ones the mass of a small mountain compressed into a region smaller than an atom, would evaporate in only a few billion years. Which means that any primordial black holes formed in the first moments of the universe, with that particular mass, would be evaporating right around now, right around our cosmic era. We have never directly observed one. They may not exist. The conditions in the early universe may not have been quite right to make them. But if they do exist, then somewhere in the dark of space tonight, tiny black holes the size of a single atom may be quietly evaporating, ending their long, slow lives by giving off a final burst of Hawking radiation that would, for a moment, briefly outshine the surrounding stars. We are looking for these bursts. We may someday catch one. The cosmos, even at its smallest, may still have soft surprises in store. I love the gentleness of this idea, that black holes may come in such a range of sizes that some of them are smaller than the particles you breathe, drifting invisibly through the dark spaces of the universe, gently evaporating, ending their lives in soft flashes of light that no one ever sees. The cosmos is full of these quiet possibilities, things that we have never seen, but that may be there, doing their quiet, patient work in the great dark. The black holes, even at their tiniest, are part of that quiet possibility. And if it moves you, even a little, to imagine all these strange and gentle objects scattered through the cosmos, the huge ones holding galaxies together, the small ones quietly ending their lives in soft flashes, the medium ones embracing each other across the dark in slow gravitational dances. Then, I would gently invite you to do something. In the comments below, if you like, you might leave a single word or a single sentence that the black holes of tonight have given you. Something simple, a word that lingers from this quiet drift, a feeling you want to mark, a soft note from the night. The words will gather here among everyone else listening tonight, a small, quiet chorus of people who have spent some of their evening thinking gently about the strange and beautiful objects we share the cosmos with. A small, soft community of attention gathered in the dark, all listening together to the same patient truths. And then let the thought go and return to the slow, gentle drift and to the quiet truth of these soft, cosmic things. I want to add one small, soft thought about the range of black hole sizes, because I find it gently moving when I consider it carefully. We have spoken of supermassive black holes at the centers of galaxies, with masses of millions to billions of suns. We have spoken of stellar mass black holes, the remnants of dead stars, with masses of a few to a few dozen suns. We have spoken of the smallest possible black holes, the hypothetical primordial ones, smaller than an atom. But there is also a category between these, the intermediate mass black holes, with masses of hundreds to thousands of suns that astronomers have been searching for and only recently begun to find evidence of. These intermediate black holes may form in the dense centers of star clusters, or through the slow growth of stellar mass black holes that gather mass over time, or through other processes we are only beginning to understand. What this means is that the cosmos contains black holes at every scale, from the unimaginably small to the unimaginably large. They are a kind of cosmic family, with members of every size, scattered through the universe, each playing its own quiet role in the grand, patient structure of things. The biggest hold galaxies together. The medium ones may seed the growth of the largest. The smallest may evaporate quietly in the dark, ending their lives in soft flashes of light. The whole range of them, together, makes up a population of cosmic objects that is far more diverse and gentle than the popular image of the black hole suggests. I find this lovely, in the way I find all such diversity in the cosmos lovely. The universe rarely makes only one of anything. It tends to make populations, collections of related objects at every scale, doing related work at every scale, contributing in different ways to the great, patient structure of everything. Black holes are no exception. They are not a single type of object. They are a family, with members of every size, scattered through the cosmos, each doing what its particular mass allows it to do.
The supermassive ones hold galaxies together. The smaller ones make Hawking radiation more quickly. The smallest hypothetical ones flash and vanish. The medium ones may someday teach us about how the largest grew. Each contributes its own small piece to the cosmic story. And in this gentle diversity, the black holes belong to the universe in the same way that everything else belongs. They are not invaders. They are not monsters from elsewhere. They are part of the cosmos at every scale, part of its long, patient history, part of the structure that has been here from very near the beginning and will be here in some form for a very long time to come. They are family in the cosmic sense. Family of every size, doing family work at every scale, holding things together, ringing softly when they meet each other, evaporating gently when they are small, anchoring galaxies when they are large. You live in a cosmos full of these gentle relatives of every size. They are scattered through the dark, doing their patient, quiet work. And tonight, somewhere in the dark, all of them are doing exactly what they have always done. I want to tell you, gently, about one of the most beautiful pieces of the physics of black holes. A feature that astronomers call the innermost stable circular orbit, or sometimes the ISCO. It is a quiet feature of the geometry near a black hole, and it is one of the loveliest things I know about them.
Around any massive object, a star, a planet, a black hole, you can orbit in stable circles, provided you are far enough away. The further you are, the slower and gentler your orbit. The closer you get, the faster you must move to stay in a stable circle. This is true around the Sun and around the Earth and around our small moon. It is also true around a black hole. But near a black hole, something strange and wonderful happens that does not happen around any other object in the universe. There is a closest possible stable orbit, a radius below which no stable circular orbit exists at all. If you try to orbit a black hole closer than this innermost stable circular orbit, no matter how carefully you set up your trajectory, your orbit will not be stable. It will spiral inward, gently, gradually, toward the event horizon. There is no way to balance the gravity at that distance. The geometry of space simply does not permit a stable circle there. You can fall, or you can climb away, but you cannot stay. I find this exquisitely beautiful. For every black hole, there is a last possible stable circle. Beyond it, you can rest in orbit for as long as you like, drifting peacefully around the black hole, the way a planet drifts around its star. Inside it, you cannot rest at all. You either fall or you go. There is no in-between. And this turns out to be one of the most important places in the universe for understanding what happens to matter that falls toward a black hole. The accretion disks we spoke of earlier, those luminous rings of hot, glowing matter around feeding black holes, have an inner edge that lies right at this innermost stable circular orbit. Matter drifts inward through the disk, slowly losing energy through friction with itself, slowly spiraling closer until it reaches that final, stable circle. And then, having reached the boundary beyond which no stable orbit exists, it simply lets go and falls. The final plunge into the black hole begins at the innermost stable circular orbit, the last quiet circle, the last place where rest was possible. After that, only the long, quiet fall toward the future. There is something almost prayerful in this geometry. Every black hole has, written into its very mathematics,
a last quiet place, a last possible rest. And beyond that last rest, everything must move on, must release, must fall toward whatever the center holds. I do not know if this is something we can apply to our own lives, but I find it tender to consider as I lie in the dark thinking of it. Even the most relentless, most gravitationally extreme objects in the universe have, somewhere in their geometry, a last quiet place to rest. The cosmos is generous in this way. Even at the very edge of what is possible, there is one more circle, one more place where things can hold themselves together for a while, one more soft pause before everything else has to flow onward. And if you would like more of these quiet drifts through the cosmos to find you on other nights, subscribing is the surest way to let the next one come. The Voyagers were built to keep on faithfully arriving. These nights try to do the same in their own small way. Then let the thought go and let yourself drift onward toward the last quiet stretches of the night. Let me say one more soft thing about the innermost stable circular orbit before we leave it. Around a non-spinning black hole, the radius of this last stable orbit is 3 times the radius of the event horizon. So if a black hole has an event horizon 10 kilometers across, the innermost stable circular orbit is 30 kilometers from the center. Inside that 30-kilometer radius, no stable orbits exist. Matter that falls into that region plunges inevitably inward, no matter what its trajectory is. The 30 kilometers is, in a sense, the last shelf of stability, the last place where anything can rest, the last small circle of peace before the long, final fall. Around a spinning black hole, and most real black holes spin because they form from spinning matter and have angular momentum, the geometry is more complicated. Spinning black holes drag the space around them along with their rotation in a phenomenon called frame dragging. The innermost stable orbit for a spinning black hole can be much closer to the event horizon than it is for a non-spinning one, depending on whether you orbit with the spin or against it. If you orbit against the spin, the innermost stable orbit is further out. If you orbit with the spin, you can get closer to the horizon before the orbit becomes unstable. The geometry of spinning black holes is one of the more elegant pieces of mathematics in general relativity, and it has consequences for how the accretion disks around them look, and for how much energy they can release.
And in their birth, in the great supernova explosions that mark the death of a massive star and the formation of a black hole, enormous amounts of matter are flung outward into the surrounding galaxy. The heavy elements, the carbon, the oxygen, the iron, the calcium, the gold, all of which had been forged in the heart of the dying star, are blown outward into space by the violence of the collapse, scattered through the surrounding gas, mixed into the great clouds from which new stars and new worlds will one day form. Every atom of iron in your blood, every atom of calcium in your bones, every atom of carbon in your hands was forged in a star that died this way. Some of those stars left black holes behind. Others left smaller remnants, neutron stars, white dwarfs. But all of them gave their atoms to the cosmos to be gathered later into worlds and minds, and you, here, in this quiet room, tonight. The black holes of the universe are not just endings, they are also beginnings. They are the markers of stars that, in their dying, gave the cosmos the heavy elements from which life and worlds eventually form. We are made, in part, of the deaths of stars that became black holes.
We are made of the same long story that gives the cosmos its dark gravitational anchors. The black holes and we are part of one single quiet history, the long, patient cycle of stellar life, stellar death, stellar gift, slow gathering of matter into the new things that come after. And if these nights bring you any peace, subscribing is the easiest way to let the next one find you on another quiet night. The black holes have been quietly carrying out this slow, patient work. The dying of stars, the gift of heavy elements, the gentle holding together of galaxies for billions of years. These videos try, in their own small way, to keep arriving, faithfully, for as long as they can. Then let the thought go, and return to the gentle dark, and to the slow truth of what black holes really are. I want to dwell here, in this gentle thought about stars and black holes and the elements of our bodies, because it is one of the most quietly moving truths in all of astronomy. The atoms that make up everything you love, including yourself, are not original to the universe. The cosmos did not begin with carbon or oxygen or iron or calcium. The cosmos began, after the Big Bang, with mostly hydrogen and helium, and almost nothing else. All the other elements, the ones that make rocks and water and trees and bones and minds, had to be made. They were made in the hearts of stars, by the slow, patient nuclear fusion that powers stellar life. And they were scattered into the cosmos by the deaths of those stars. Some of those stars went on to become black holes. Others did not. But all of them, in their dying, gave the elements they had forged back to the surrounding galaxy, where the elements gathered into clouds, and the clouds eventually condensed into new stars. And around some of those new stars, new worlds formed. And on at least one such world, life arose. And after billions of years, that life produced you, here, in this room, tonight, listening to a soft voice tell you about the elements in your own body and where they came from. You are made of starlight, in this very literal sense. Every atom of carbon in the proteins of your body was forged in the core of an ancient star. Every atom of oxygen in the water you drink was made in the same way. Every atom of iron in the hemoglobin that carries oxygen through your blood. Every atom of calcium in your bones. Every atom of zinc and copper and magnesium and the trace elements that make your cells run. All of it was made in stars. Some of those stars left black holes behind. Others left smaller remnants. But all of them, in their deaths, contributed pieces of themselves to the great cloud from which our solar system was eventually built, 4.5 billion years ago, in this small, quiet corner of the Milky Way. The black holes of the cosmos, then, are not separate from us. They are part of our own deep history. The stars that died to make us, some of them became black holes. The cosmic events that gave us our elements, they were the same events that gave the cosmos some of its black holes. We share an ancestry with these dark, gentle objects. We are made, in part, from the same long story. The atoms in your fingers and the black hole at the center of some distant galaxy are, in a sense, cousins, both born of the same patient cycle of stellar life and stellar death, both products of the long, slow universe that has been turning since the Big Bang. We are family. The cosmos is family. The black holes are part of that family, in their own quiet way.
And I find something gently beautiful in remembering this, especially at night. The dark objects scattered across the cosmos are not strangers to us. They are part of the same long story we are part of. The same nuclear fusion that made our atoms also made the bright phases of stars that, in the largest cases, eventually collapsed into black holes. The same supernova explosions that scattered our elements into the cosmos also created some of the cosmos's stellar mass black holes. We are not separate from the dark anchors of the universe. We are made, in part, of the same long history that produced them. We belong to the same cosmic family. And tonight, as you rest, the cosmic family is still doing what it has always done: turning, fusing, dying, scattering, gathering, beginning again. The cycle goes on. The cycle has gone on for billions of years. The cycle will continue, gently, long after we are gone. And the black holes are part of that cycle, family of ours in the deepest cosmic sense. So, as the night deepens around you and sleep draws near, let us gather everything we have understood tonight, gently, into one last quiet thought. We began with what we had been told about black holes: that they are monsters, that they hunt, that they suck, that they devour, that they are dark holes in the universe, empty pits, voids that swallow everything. And piece by piece, we have seen that almost none of that is true. Black holes do not suck. Their gravity reaches no further than the gravity of any other object with their mass. If our sun became a black hole tonight, the Earth would keep orbiting peacefully, as it always has. Black holes are not holes. They are concentrations of matter and energy so intense that the very fabric of space curves around them. They are the fullest, densest, most concentrated places in the universe. Not absences, but presences, packed into small regions of space. Black holes are not dark. The black hole itself is dark, but most of the black holes we observe are wrapped in extraordinary luminous accretion disks, blazing with light brighter than entire galaxies, sometimes shooting out enormous beams of glowing matter that stretch for hundreds of thousands of light-years across the cosmic dark. Black holes do not devour galaxies. The supermassive black holes at the centers of galaxies are, instead, the gentle gravitational anchors around which the galaxies turn. The one at the center of our own Milky Way, Sagittarius A star, has been holding our galactic home together quietly for billions of years, and will continue to do so for billions more, asking nothing of us but our occasional, patient attention. At the edge of a black hole, the largest event horizons are not violent places, but smooth and peaceful surfaces, places where the geometry of space changes so gently that you could cross without noticing. Inside a black hole, the strangeness is not that you are pulled in, but that inward becomes in time. The center of the black hole becomes your future, and you fall toward it the same way you fall toward tomorrow, in the gentlest mathematical sense. Black holes meet each other. They embrace, they merge, and when they do, they release soft ripples of gravitational waves that travel across the cosmos, soft cosmic chirps that we have learned, finally, to hear. Black holes are not eternal. Slowly, patiently, across spans of time too vast to picture, they evaporate, giving everything they have gathered back to the cosmos. Even the supermassive ones will, eventually, return their gathered matter to the great, patient quiet. Black holes do not erase. Nothing that falls into them is truly lost. Somewhere, somehow, in the soft drift of their Hawking radiation, in the patterns on their event horizons, all the information of everything they ever swallowed is gently preserved,
and slowly released back to the universe. Black holes are not isolated. They come in every size, from supermassive giants holding galaxies together to tiny primordial ones smaller than a single atom, drifting invisibly through the dark. Black holes are not separate from stars. Every stellar mass black hole was once a shining star. They are the soft, final forms of the most massive stars, the quiet graves of beings that once gave off light. And in their birth, in the great supernova explosions, they gave the cosmos the heavy elements from which we ourselves are made. We are made, in part, of stars that became black holes. We are part of the same gentle history.
This is what black holes really are. Not the monsters we have been told they are. Not the destroyers, the devourers, the void. Something stranger and softer and more beautiful. The dark anchors of galaxies, the soft graves of giant stars, the quiet preservers of cosmic information, the makers of the heavy elements in our blood and bones, the slow, gentle ringings of gravitational music, the temporary cosmic objects that will, in the fullness of time, give everything back. You live in a cosmos that has black holes at the center of every galaxy. You live in a cosmos where black holes have been quietly making the heavy elements of your body for billions of years before you arrived. You live in a cosmos where two black holes embrace each other across the dark and ring it like a slow, gentle bell. You live in a cosmos where even the most concentrated, most extreme objects are temporary and patient and gentle, and ultimately willing to give everything back. There is nothing to fear in the dark center of your galaxy. There is nothing to fear in the great gravitational anchors of the cosmos. They are not the monsters we have been told. They are quiet, patient features of the home you live in, doing the slow work that keeps everything in place, holding the galaxies together, forging the heavy elements, ringing softly across the dark when they meet, returning everything they gather to the cosmos in the long, patient eons. So let the truth of them carry you gently towards sleep. The dark anchors of the cosmos, the soft graves of the giant stars, the quiet, patient mothers at the centers of galaxies, the gentle music of gravitational waves, the slow returning of everything to the great cosmic quiet. The black holes are out there, tonight, doing their patient, gentle work, holding the universe together, asking nothing, ringing softly, and ultimately giving everything back. They are not what we have been told. They are something far stranger and softer and more beautiful. Sleep well. The black holes of the cosmos have been quietly doing what they truly are for billions of years already. They will go on doing it, gently and patiently, for billions of years to come, holding the galaxies, forging the elements, ringing softly in the dark. And the great quiet that holds them is the same great quiet that holds you, here, tonight, in your small, warm bed, in your small, warm room, on your small, warm world, in your small, warm, gentle corner of a cosmos where even the most fearful objects are, when you look at them gently, full of slow, patient beauty. You are not in a cosmos of monsters. You are in a cosmos of patient, quiet wonders. And tonight, all of them, even the ones we used to fear, are simply being what they truly are, gently in the dark around you while you rest. So as you drift, let the truth of these things settle as softly as it can. The dark places of the universe are not enemies. The most extreme objects in the cosmos are not threats. The supermassive black holes at the centers of galaxies are not waiting to devour you. The event horizons are not violent walls. The interiors are not torture chambers. The gravitational waves are not warnings. The Hawking radiation is not a curse. Every single thing we used to fear about black holes turns out, when we actually look at it, to be something quieter, gentler, more patient, and more beautiful than we had imagined. This is what science gently does when it is allowed to. It takes the things we have feared and looks at them carefully, and shows us that the world is, almost always, more interesting and less frightening than the stories we tell about it. Black holes are perhaps the most striking example. They were, for most of the 20th century, almost universally feared. Now, in the 21st, after 100 years of patient observation and patient calculation, we know better. Sleep well tonight, in this cosmos of quieter truths. The black holes are out there, doing their patient work, asking nothing of you, ringing softly in the dark when they meet, anchoring galaxies, scattering elements, evaporating gently across spans of time too long for any of us to imagine. They are not what we have been told. They are something far stranger, softer, and more beautiful. Good night, dark anchors of the cosmos. Good night, soft graves of the stars. Good night, gentle mothers at the centers of the galaxies. Good night, you.